All right, good deal. Why don't we go ahead and get things rolling? We're at 8:03 here. So welcome to the 50th Midwest Manufacturing Leaders event. So we started out at Queenie Park about 9 years ago. Thanks, Don, for the round of applause there. Started out at Queenie Park about 9 years ago hosting these events. If any of you are not aware, there's a website, MML, Midwest Manufacturing Leaders, mmlgroup.org. And out on that site, you can see all the past events. You can see all the videos from the point in time that we started actually recording the events. But there's a wealth of really good information out there and really good data to share with anybody that you know that's in the manufacturing space. So with that, we want to get things kicked off today. Please do post any questions that you have in the chat. When you're doing that, please make sure that you have everyone selected so that we can see those questions come up, and we'll get those answered as we go through here. So with that, Andre, Mike, and Andy, I was going to let you guys kind of do a little intro of yourself when you each come up. So with that, I'd like to kick it over to Andre Casto from SLU CAM. Andre, the mic is yours.
Thank you for that introduction and letting us talk to all of you. So just a quick introduction here. So I'm Andre Casto. I'm the lead engineer at the center. So I run the day-to-day operations. So if you contact someone, it's probably going to be me. And then we help facilitate any connection with any of the resources that we have and anything that you want to use. Andy, would you like to introduce yourself? Nope. All right. Well,
look like Andy might be on mute.
The classic problem.
No worries. 21.
Yeah. So anyway, I teach biomedical engineering at SLU, and I'm also working with Andre as part of the leadership team for the center. Glad to be here.
Thanks, Andy.
And then Mike made it clear that he wanted to try to not to speak too much. So Mike Hill is also here. He can answer questions if you have them. But he is the president of Hill Innovations and also one of the great examples of the type of people that we've recruited to help advise our center.
Yeah, thanks, Andre. I will say a little bit about myself. Does that sound arrogant? I apologize if it does. So yeah, president of Hill Innovative Solutions. We're an engineering service business, and then we've got 3 sister companies that are in the manufacturing industry, and that's where I get to help out with SLU CAM and as an advisor. They graciously let me voice my opinion on things and from a manufacturing perspective, and that's the exciting part for me about this and being able to talk to everyone about this is that this is such a tremendous resource for manufacturers in the St. Louis area and manufacturers kind of nationwide also. So I'm excited. Like Andre said, I really don't want to talk much because this is really Andre and Andy's baby. But I did want to chime in and let everyone know that this is a tremendous resource for everyone.
For that, Mike. So if you're not familiar with additive manufacturing, it's really just a fancy way of saying 3D printing. So we run some high-end 3D printers as well as some other equipment, CAD work, 3D scanners, just to help facilitate, 1, research at SLU, and 2, connect the technology with people who might be interested in using it, but don't have the capital to invest in it. So I'd like to just give a little brief overview of some of the state of additive manufacturing in a couple different areas. So obviously we're in academia, so we always start there. There's been a huge investment in teaching and purchasing equipment in the academic space, and this includes all the way down to grade level. So early childhood development are using 3D printers to make toys and interesting objects to help with teaching, all the way up to the academic level, who are the collegiate level, who are developing new printers, new technology, and coupling with corporations to help get these out there. So there's a huge investment. We always like to look at publications. So this is a plot of the last several years and the number of publications. So you can see the technology has really taken off in the last 10 years or so. We're averaging over 7,000 publications per year. And then who's investing in these publications? Some of the big names, the NSF, the NIH, are typical funding agencies for academia, but also notably the DoD, the Air Force, the Office of the Naval Research. So there's huge government investment in this technology as well. So I don't expect you to take away anything from this slide. I don't expect you to be able to read it. But I do want to highlight a couple things. So there are several different types of materials. So each of the big squares here that are filled in is a different technique. So the types of materials are polymers. So these are going to be your plastics, your resins, and thermoplastics. There's composites, metals, biological applications or biological inks, and then cement and ceramics. So your more architectural applications. The only takeaway that I want you to take from this slide is that all of these little circles or all these little dots on the outside are all different companies that sell 3D printers. They're not even the number of printers that they sell. They're just different companies that sell different printers. And these can cost from the hundreds of dollars to the millions of dollars. All right. And as you increase costs, you increase reliability. So what are those companies? Who are those companies selling to? Obviously, a wide range of people, with the big players being the aerospace, consumer products and electronics, and then a huge application in the medical and dental realm. And then the other key thing that a lot of people like to look at is the market size and the projections there. So we can see that it's a rapidly growing technology with high adoption rate and then a high growth rate. So
oh wow, good job, honey.
The projected market cap in the next couple of years is upwards of $20 billion. So there's obviously a lot of room for growth and a lot of room for application. So I'd just like to highlight a couple of those major adopters. It's always, you can look at a pie graph like this and say, oh yeah, the automotive industry is using it, but what are they using it for? How does it affect me?
You have it. You have all the pieces.
So some of the major adopters that I'd like to highlight are the aerospace, the automotive, and the medical applications. So the aerospace, some of the big names that are using it: Boeing, NASA, Lockheed Martin, SpaceX is using it. Boeing's using this for production parts. So they have over 300 flyaway parts that they incorporated into their planes. Obviously, this is nothing structural yet. These are mostly internal components, parts for the chair, the seating, parts for ductwork and ventilation. So every customer for Boeing has different requirements. So the number of seats they want, spacing on the seats, arm room, leg room. So obviously, if you want the ventilation to accommodate those different requests, you need to be able to make those parts rapidly and customize. So this is a perfect application space for additive. Another perfect application is, oh, sorry, go ahead, Mike.
I do want to chime in there on, because, 10, 15 years ago when we were using additive manufacturing, it was, there was the misconception that it can only be used for prototyping, and you see the material advancement that I know you have later in your presentation, but I think that this is a good part to highlight, is that it is being used in more of a production realm now, in actual final application, not just prototypes, not just first betas or anything like that. This is actual production parts, flying parts.
Yeah, and just to highlight that, NASA's using additive parts on their rovers and their space station. So the Mars rover that just landed what are we looking, a month ago now, maybe 2 months ago, it had 5 distinct additive produced parts, and they sent that millions of miles away and are relying on those parts to function in a completely different space. So we are working past prototyping and more into a production sense. Thanks for that point, Mike. The other space, and this is back more towards a prototyping option, is the automotive. So they're using it to design more efficiently. So obviously, as the push for a greener, more sustainable world, that's going to come in the sense of lighter parts, more efficient parts. So Volkswagen's a good example of that, using generative design and 3D or additive or 3D printing to produce these custom, super lightweight, super efficient parts for their electric fleet. And then the last space that is really well fitted for additive, since you need customizations for every part, is the medical. So surgical guides, dental applications, and prosthesis are great applications because you can do a custom or patient-specific development. So the key takeaways from the last couple slides is, one, it's a rapidly growing technology. It has a huge range of applications. The largest companies are investing heavily. We're talking millions, billions of dollars of investment over the last 10 or so years, with more to come. With the biggest investments coming in the expense of the machines and infrastructure upgrades. So that can be ventilation, safety considerations. It is known as an industry disrupting technology, and that's because it's disrupting all things from supply lines all the way to production and how you produce and get your part out the door. So you may be thinking to yourself as a small manufacturer, where do I start first? How do I get involved in this technology? So you've got several options. One, you could buy a cheap entry-level machine that's going to be in the hundreds of thousands of dollars. You're going to have limited material. It's going to be semi-reliable, and you're going to have little to no support from the manufacturer of the printer. So it's going to be up to you to learn the technology and incorporate it how you see fit. Another option is print farms or service bureaus. They're not collaborators. They just want to take your file. They want to print it. So you already need to know something about the space, the applications, limitations, how to design for additive, which is different than designing for traditional manufacturing. And it's going to get sent to a place like this. You know, they just have rows and rows of printers. They have couple people that run those printers and maintain them. They're not looking too thoroughly at your part before they print it. They're just assuming that you know what you're doing. The other option is that you can invest in the technology. So you can spend tens to hundreds of millions of dollars in a nice, reliable system. You're going to have good support. You're possibly going to have to upgrade your infrastructure. This could be ventilation, humidity control, other safety factors. But if you're not ready to make that leap, you could come talk to SLU. So we've done that investment for you in order to, one, help train our students to better prepare them for the future. And by offering this to the local community, we're hoping to have better examples to help teach our students. So that brings us to what SLU is. So we're a resource to the community and to SLU to help bring additive technology and make it available to anybody who's interested in exploring it. So our primary mission is to educate. So if we can develop relationships with the community and what they're using this for, we can better educate our students to go out into that workforce. So where we're located at 240 North Grand in a new interdisciplinary science and engineering building that was just opened last year. It's shown here on the left. It's a nice new shiny building that's focusing mostly on the sciences and engineering as stated in the title. We were given about 1,000 square feet in this facility in which we house a full-time engineer. We have several student worker spaces that we employ to help train. We've got 4 commercial grade 3D printers, 2 commercial grade laser cutters, and then all the post-processing requirements that we need to help bring those parts to life. So this is what we actually look like. It's a fairly small space, but we have all the big technologies. We're open daily from 9 to 3. Hopefully hoping to expand those hours as things open up more as COVID goes away. What do you do first when you're in an additive space? You 3D print your facility, right? So this is one example of the type of things that we can print. So we can print nice, realistic models in full color and even clear materials. So this is all directly off the printer. This is how it came. A couple student workers that we have. Actually, all these people will be rotating out shortly. We'll get a new batch of student workers this fall. But we'll keep 2 to 3 student workers on staff. So if you do reach out, you'll probably connect with myself. And then depending on what the project is that we develop, we might switch it to one of the students to help train them. I'm not sure how familiar you guys are with the additive space, but we did invest in 2 of the big technologies. One is FDM printing. It's a thermoplastic technology. So it works exactly like a hot glue gun, except for it's on an XYZ gantry. And it allows us to print thermoplastics. We can print basic prototyping plastics such as ABS and ASA, and then more functional, durable materials like the stuff that Boeing's using, polycarbonate, nylon, carbon fiber infused, and PEC. Most of our systems do have a sacrificial support material, which aids in post-processing and getting your part out the door faster. So a lot of our parts, when they come off the printer, we can throw them in a bath. It's going to dissolve away any of the support material. The only post-processing that you're left with is just some sanding or finishing that you might want to see if you don't want to see the layer lines, and then any painting or detail work that you would want to see. Some of the advantages of FDM printing: you can produce strong, robust parts. You can produce pre-assembled mechanical parts. It is considered a lower resolution technology with layer heights about 300 microns. So you will see these layer lines as compared to traditional manufacturing where you don't typically see your tooling marks. The limitations include it's a one material per part, so you're not going to make that cool multicolor part that I showed you a couple slides ago. You are going to see those layer lines and need to do some surface finishing if you want a nice, show and tell part. And then the support material can be complicated, so it does have to go in a caustic bath. It's got to sit in there for a while. The more intricate your part, the longer that takes. But typically what we're looking at is for the average part, we're looking at about a day to print and maybe 2 days of post-processing. So once you've got an idea and you've got a file, we can typically give you something within a week. And we've got a couple different printing options, and we can talk about these later. The key takeaway here is that we have high-performance thermoplastics, and we have a fairly large build volume. So 406 by 350 by 406 millimeters. That translates to about 16 by 14 by 16 inches. And then this is just a couple examples. So we helped with the PPE crisis, obviously, as COVID hit. This is an example of a ball bearing that was all printed in place, so there was no assembly afterwards. This does actually rotate, and it's fully functional. And then we've done a little bit of art printing and then a little bit of model printing for the engineering department. The other technology that we've invested in is a very good prototyping. So this is for making hyper-realistic models. So it's called polyjet printing. It works exactly like a desktop inkjet printer. The only difference is instead of printing with an ink that's colored, you're going to print with a photocurable resin and build up materials. So the benefits of this technology, just like your desktop printer, you can get the full color spectrum as well as multiple material properties. So we can print from clear hard plastics all the way to opaque hard plastics, all the way to clear and opaque rubber-like materials. And again, this does have a sacrificial support. So again, post-processing is fairly minimal. We just went over those advantages and limitations. The key takeaway here is it's higher resolution. So the layer height's about 150 microns the layer height's about 14 to 27 microns, which means that you're not going to typically see these layer lines once it comes off. That removes some of that additional sanding or surface finishing that you would need to do. We do have two polyjet technologies. The one that most people would be interested in supports up to 6 materials, so we can get the full color spectrum as well as multiple diameter materials out. And it does have a fairly large build volume at 350 by 350 by 200 millimeters. And then this is just like an example of some of the things that we've printed. So we've got obviously the full color spectrum that is highlighted by the center figure here. We've got clear materials, as you can see by our logo with the Billigan and the SLU cam encased in a clear resin. And this is how it came off the printer. So there was no post-processing. This is as clear as it gets. If you need it to be a little more clear, you can do some surface sanding and lacquering in order to make it a little more clear. The other thing that we use this for is microfluidics, which we can embed either electronics or wires into the print during the printing process to add a little bit additional functionality to it. Post-processing, like I said, it's mostly automated, so we have a fairly small room for it. We have a caustic cleaning bath that we drop everything in, and then polishing, painting, and surface finish are pretty much the extent of your post-processing requirements. The other technology that we do have in-house is laser engraving. So we have an Epilog and a Glowforge laser cutters. They are fairly high resolution, and we can cut all the way up to thick plastics. And with the Epilog system, we can mark some metals. So if you're interested in that, we can chat about that later. We're going to focus mostly on the 3D printing. The last technology that we offer in-house is 3D scanning. So the ability to take a part that maybe is discontinued, we can reproduce that, and then we can replicate it on the 3D printer. So that's a great application of the additive space, is looking at discontinued parts or parts that are hard to come by now. So in summary, we offer 3D printing and laser engravers. We do help with the design work, and I didn't highlight that before, but all of our students are trained in SolidWorks and other design programs in order to help produce your part. So if you're not even sure on where to design, we can help with that. And also we think additively, so we're trained in designing for the additive process, not necessarily for traditional manufacturing, which can be very different. And then 3D scanning, so we can scan full color and full texture files in order to print them on either printer. A little bit about the logistics of how to connect with us. So you can reach out via email or on our website. We do have a "You Can Book Me" link. If you want to sit down and chat, you can either come into the center or we can set up a virtual call. So our initial discussion will either be in person or over Zoom. We'll walk you through what we offer, make sure that your goals align with what we can help you with. Then we'll set you up with a GrabCAD shop account. This is an online portal where you can track the progress of your parts. So you'll submit your parts through there. It'll get assigned to one of our workers, and then we'll update you as we go through and review your file. We'll approve it. We'll send you a quote. Once we approve the quote, then you can trace it through printing, post-processing, and then eventually ready for pickup. I'm not sure. Sorry, I didn't see any of these questions come through. Doesn't the part need to go through certification before it end up on a plane or a tank or vehicle? Yeah, so I don't personally know much about the certification process, but there are regulatory bodies that are looking at this. And I know that Boeing does have approval for their flyaway parts. Most of them are all in plastic. And I have heard that they do have some metal parts that are in the approval process, but I don't know the details on those regulations.
Yeah, and you know, every application is going to be unique, Andre. You know, the materials themselves will carry their own material certifications, and then the part design and configuration will need to get its you know, its authority certification and everything. So it is kind of a case-by-case basis, but a lot of the materials, especially the higher end materials that Andre mentioned, they already have the material certs from, like I know the Ultim material carries its FTS certification with it. So there are certs that go with the materials, but then there's also certs that go with the parts and the application.
Thanks, Mike. And that's why we have advisors, right? So our billing, we do bill for our services, and it's mostly because of the investment in the technology. So we bill based on the cost of the material and then consumables for the printer, plus some small markup that covers failures. So we're pretty transparent about our billing process, and we do, I'd like to show a comparison between our billing and then a commercial or service bureau. So we trend to be significantly cheaper, and that's mostly because we're trying not to make money per se off this technology, but really to offer our students the option to get trained in it, right? So we're more focused on education. That's our primary focus. So we want to be able to have these cases or these examples that we can share with the students.
Well, and again, I want to, you know, piggyback on that, because you think about it from the industry side, and the, you know, getting that talent and that know-how. You know, a few years ago, Northrop Grumman came out and flat out said, if you're not using additive manufacturing, you're already behind the curve. You know, and so to have students and that knowledge base that you're able to tap into while they're still, you know, in school, and as a, you know, as a potential future employer, to have that knowledge base, especially in kind of the talent struggle that a lot of us companies are having right now, getting talented individuals. And then now you've got talented individuals with know-how of future technology, or technology that is really here now, is very valuable.
So we'd just like to spend the rest of the presentation just talking about through a couple examples that we have, to kind of showcase what additive can do for you. So one of the big ones that we helped with was user-specific N95 respirators. Obviously, a lot of people jumped on this right at the beginning of COVID. There was a lot of bad information and mixed results with the possibility of 3D printing a mask, and a lot of misinformation about what it was capable of. So as COVID crisis started, we were looking at supplementing N95 respirators. So the requirements for an N95 are much more rigorous than a surgical mask. So I've shown them both here. A surgical mask is fairly flimsy. It's probably what most people are familiar with right now. It's comparable to what your cloth masks are if you're using those. An N95 mask, on the other hand, has fit requirements, so it needs to seal around the mouth in order to prevent any contamination getting to the user, right? So a surgical mask is more about protecting the people around you. An N95 mask is more about protecting yourself. All right, so we just assembled a team, 3D printing scientists, a CAD expert, and then a couple of engineers who were interested in tackling this problem. And with the additive process, in the morning, we were able to assess a prototype. So we printed it the night before. In the afternoon, we were able to meet and discuss virtually, obviously. And then in the evening, we were able to set up and print a new design. So we started with something fairly crude. We wanted to do a patient-specific model. So we went through and we scanned several people. We made a crude model of a mask to make sure that we could subtract out that face to get a perfect seal around the face, even though it was made out of a hard plastic. And then we iterated through design. So we found out that we didn't get a good seal around the nose, so we elongated the design. We didn't get a good seal around the cheeks, so then we ended up widening the design. And then we added some features. So we needed hinges on here in order to attach straps. And then we wanted a replaceable filter. So we added some threads on here. So we were able to mock up these designs, print them that night, and then reassess the next day. So that's one of the huge benefits of additive, is how rapidly you can iterate your designs. So with a small part like a mask, obviously that's about the size of your face, we can print a batch of those. So I think we were printing 9 at a time. We can print that overnight. So that was about a 16-hour print. So you come in about 5 in the evening, you load them up after you've made your design changes, and then they're ready to be looked at the next morning. So with this, we finally settled on a design that looks like this. You can see that we've iterated through a perfect nose bridge. We've got a nice brim around here to give a good seal around the face. We've got a filter material that was still available. So by making our own custom mask, we could look at what filter materials weren't already out of stock and which ones were easily made. So the option that we chose was a flat stock material that could be rapidly produced and was upscaled greatly during the COVID crisis. And then we had a cap on here that we could screw on. And now we could print up to 9 of these, the top and the bottom, on our printer overnight. So we could iterate these very quickly. The other thing that we did was we took the face and we subtracted it out of this brim of the mask so that we got a perfect seal for every user that we needed. So what we had to do is we had to go through and scan everybody. So the actual workflow to making this mask only took about 4 hours, about an hour to scan, about 15 minutes to do the processing. And then if you had 9 of them, then you'd have to multiply that by about 9. So the backside of the mask looked like this. You can see the blue part here shaded in is where the face was actually subtracted out of the mask. So you had a perfect fit for every person. And then this is someone wearing our mask who's actually getting a quantitative fit test. So that was the other thing that we wanted to do, is we wanted to make sure we thoroughly tested this mask to make sure that it performed at or better than an N95, and we did meet that requirement. The other thing that rapid prototyping allows us to do is we had a couple complaints from bigger people that they couldn't breathe. So we were able to explore other filtering options. So we had a P100 filter, which is better than an N95 filter material. So we made adapters for those. So if there was a shortage in the filter material that we chose, there were other options that people could use. And then we were able to explore larger surface area options. So if people had trouble breathing, we could put an adapter on their current mask, in which they could put a larger surface area filter or a pleated filter in to allow them to breathe more easily. The key takeaway here is that we did receive hospital RIB approval for wide distribution at the hospital. It ended up not being necessary because masks became widely available again. We did successfully test on 15 users, and we had a 14 out of 15 pass on the first iteration. The 15th person was a smaller person, so we hadn't made a mask that was small enough for them yet, but obviously we could go back and iterate that. But really the key takeaway here is that we did this all in 6 weeks. So we went from project idea to founding a group to a workable product in 6 weeks. And then I think Andy's going to talk about how he's using 3D printing or additive manufacturing for some of his robotics research.
I'm glad to do that. Also, we had a question about confidentiality. So we have a standard confidentiality agreement that we're happy to send any prospective folks. And so we'll keep any information confidential. If you want to promote it, promote the fact that you work with the center, we're happy to do that. If you want it to be like we never ever met, we're happy to do that too. So if you have a confidentiality agreement, we're happy to evaluate it. Of course, that takes a little longer, but we do have a standard agreement that we're happy to send you and work in a confidential way. So yeah, so one of the things I work on in the lab is image-guided robotic spine surgery. And so with the robot that we had shown here, the fundamental question is, can we achieve an industry standard sub-millimeter accuracy when placing spine screws and automatically? What happens now, even in robotic spine surgery, is that the final step has to be performed by a physician manually with a drill and a screwdriver, and we wanted to automate that as well. Eventually you have to end up with stainless steel end effector parts if you're going to if you're going to use this on patients. But we weren't sure that we could achieve the accuracy, and so what we wanted to do was make sure that we could before we made the significant investment in the parts. So it was really about concept validation. So go ahead, Andre, if you would. Right, so in our first iteration, well, first several iterations, I guess, we did everything with a 3D printer. So we printed the racks, we printed the tools, we printed the tool exchanger. So every single thing we did with the part, we did in 3D printing, and this off, the students did this with a CAD design and printed it overnight on an FDM printer. And so they went through about 5 different iterations of these different end effector tool parts. So go ahead, sir. And so once we got all this done, we did accuracy testing. And so this looks like a cow femur from a local butcher. And instead of putting in expensive spine screws, you can see we actually put in deck screws, but you can still validate the concept that way. And then that's our imaging platform that allows us to measure the error. And so it turns out that using 3D printed parts, we were able to achieve about 0.75 millimeter accuracy on the location of the screws. And so that, go ahead, please. Thank you. That gave us the confidence that we needed to go ahead and spend the 10K to get stainless steel parts. And so we did that. We redid the experiments. We got actually, of course, a slight improvement in accuracy. But I guess the message here is that before we invested in the technology, we used additive manufacturing to verify that it was actually going to work. So I think I have another one. Yeah, and so it ended up in a nice publication for the lab. And I guess the takeaways were, yeah, we validated this concept before we incurred a major expense. Also, we were able to quickly go through designs. Again, not unlike the mass project, you design something, you evaluate it, and then you print the new version overnight. The other really nice thing for this project and others, I suppose, is that it's a really good learning experience, not just for the students, but it also allows you to explore sort of slightly wilder ideas. There are things that if you had to invest $10,000 in making a part, you would, I think, necessarily be more conservative in your designs, not wanting to waste money. With 3D printing, you can try those crazy ideas because it takes $10 to print, not 100 or 1,000. So for manufacturers, I think it's a nice way to explore a broader field of solutions. For the students, I didn't have to sweat so much that they were spending a lot of money on crazy ideas because it was really, really cheap to print the parts.
So another interesting application that we're exploring is a joint venture with SLU. So we're looking at using their LiDAR-equipped drone to take 3D scans of the city. Specifically, we're looking at the St. Xavier College Church to 3D print that. So it's a great way to catalog old buildings or catalog things that you can't traditionally scan or design in CAD easily. So this is if you're not familiar with St. Xavier's Church, this is what she looks like. This is a picture of the drone flying around. And then this is what, if you're not familiar with LiDAR, this is what LiDAR spits out. So a LiDAR spits out point cloud data. So all of these are, anything that you see in color is a single point. If you were to scroll in, you would see about 2 inches of separation between all the data points here. So then we needed a way to convert it into a mesh and produce it into a solid object. So we can see that we've explored printing on the FDM printer, and now we're exploring on converting these colors into something that we can print full color on the PolyJet system. Another application, obviously these are going to be not manufacturing focused, but more academic, since that's where we live, is PolyJet printed microfluidics. So traditional lithography requires the use of fairly expensive lithography equipment, as well as silicone wafers. So these wafers are a couple $100s a piece. Manufacturing takes days to weeks for one design. It requires expensive wafers. And then for every design change, you need to start over. So you need to make a mold on the wafer. So you have to pattern it with traditional lithography techniques. Then if that mold doesn't hold, you have to start over. And then you have to pour some type of silicone or PDMS on top of that in order to make your device. So with using additive manufacturing, we can go from design, so working on our design, to a final product in about 2 hours. So we've drastically reduced the amount of time that it takes to produce a chip. The materials overall are cheaper, as well as the equipment investment. We're not producing hazardous waste, so in order to make these molds, we use some pretty harsh chemicals and solvents. And then we can design and test the same day. So again, just like the mass project, we can iterate through several designs in a week, and then settle on a design and be ready to do testing the next week. And then one of our first success case was working with Flipstick. It's a local St. Louis entrepreneur who was funded on Shark Tank. He originally designed this adhesive that sticks on the back of your phone. It's got a flap on it that opens up, and you can stick your phone anywhere. So he wanted a new design that was out of a more rigid plastic instead of this sheet flat stock. So what we did is we took his rough sketches and turned them into the 3D CAD representation. We helped to optimize based on functionality. So we printed him some fully functional prototypes on the J735, our full color PolyJet printer. We were able to print some samples in color that he could take to the manufacturer and show. And after we did about 4 different design iterations for him, and then now he's actually talking to injection molding companies to start getting it mass produced. And that the whole time scale of that was about 3 months. And that was the pace he wanted to go. We could have gone faster, we could have gone slower, depending on what you're looking for. But he'd reach out about every 2 weeks, and after we'd give him a design, and then he'd give us a list of changes that he'd want to see. We'd review those changes in the CAD, and then we'd print the prototype for him. One of the applications that a lot of manufacturers are using, we don't have experience with it yet, but we're happy to explore it, is 3D printed jigs and fixtures. So it helps with faster production, reduced costs, and opens up some design freedom, as well as automatic positioning. So Auric here is using this to validate their injection molded parts. So they printed this piece to hold their batch. So they've got their first 10 that come out of the mold. They want to validate and make sure they're within specs. They can actually put it on this 3D printed jig. And then they have some scanning software that comes in, and they analyze the difference, the distance and the geometry while the part's loaded in this jig in order to validate the part. Okay. The other thing is more ergonomical fixtures to hold things for mounting. So this is, I believe this was an example from GM in which they were mounting their bumper, a holder to mount their bumper. So this was the traditional design. It was machined out of metal. It was fairly heavy and hard to work with. So they designed an additive part in which it was more ergonomical to hold. It was much lighter, and they increased productivity by using this. Other examples include drill guides. So you can print the drill guide. You can even embed metal pieces in there to increase the life of the product. And that way, if you have some manual part in your production process, you can help automate that a little bit. So it's a little bit faster to align it and get that hole drilled out, and then you can move on and push it down the line further.
Hey, Andre, this is, this is another example that I think, a great, easy application, easy, foot into the door into 3D printing. Actually, one of our plants this week, I was talking with them. Right now, we're pretty backed up in our tool room, right? And what do you do with your bottleneck? And then on the other side of that, you can't find more people, right? We're having problems finding people to operate the equipment. So what we did is we went through all of our jobs and said, hey, which ones are production? Which ones are we using our machining centers to make fixtures for, that we can actually outsource the fixturing to SLU for the have them do the fixtures, because it doesn't need to be a specific material. It doesn't need to be, it's not a production part. It's for our fixtures. So, we did that just this week, looking at opportunities to relieve the pressure on our equipment. That is, to give us additional capacity for our production. So that's an example, like I said, right now, real time, that we're facing is how do we handle those bottlenecks, and what can we, where can we find, a release?
Yeah, and we've heard that from several manufacturers, that's a great space for additive, because it doesn't take up your machine shop time. It doesn't take up your expertise time. You can send it off, you can get these printed, and then it can help benefit everybody. So with that, we'd like to take any questions that you have. If you'd like to reach out, we've got a slu.cam@slu.edu that you can reach out. You can give us a call. We still do use the phone. Or you can check out our website. It's not the greatest. It's going through some reworks as SLU is upgrading some technology. So that's just kind of a placeholder website for now. Look for bigger and better things in the near future. But we've got a couple minutes that we can answer any other questions that you might have.
That was awesome, Andre. Thank you very much.
Thank you for the opportunity.
Oh yeah, our pleasure. Really, really cool stuff. So what kind of questions are out there? I've got one for you while we're teeing things up. What's the coolest thing that you've had the opportunity to work on?
I mean, I'm going to be biased on my own research, I guess, and talk about my microfluidics. I love the fact that we have a full color printer now, because obviously microfluidics are really hard to see. Some of the channels that we're printing are about 300 by 300 microns, so it's about 3 human hairs. So if you're not used to looking at them, it's hard to see. So I printed this color model that has all the channels highlighted. I'm not sure how it's going to show up, but you'll see a kind of greenish channel with some purple channels on top. We colored them differently because they're different layers within our microfluidic device. So the ability to print in full color has really revolutionized the way additive is working and how useful it can be. So I'm going to bias that way, but I mean, all of our projects are neat. The church project has really come together, and we're starting to do some really cool things with that. I could see huge applications in both the defense space as well as the local geospace applications. That would be huge. And then other projects that we've worked on that we didn't have time to discuss are the medical applications, custom printed surgical guides, and even the ability to practice on the actual patient's data. So the actual patient model is huge for the medical industry.
Wow, that's really cool. Thank you. Let's see, looks like we got one coming in on the chat. What is your capacity to produce? Are you more geared to prototype production, or do you also plan to do daily or weekly production?
Yeah, I don't know that we have a great answer for that right now. Like I said, we're fairly new, and as COVID has affected everybody, it's affected us. So we have not ramped up very quickly. We have a ton of capacity right now, especially moving into the summer. Students are going home. We have minimal summer classes, so we have a lot of space right now. So if there's something small scale production that you need, we're definitely able to accommodate that now. And if the demand persists, then we anticipate investing in more technology and bigger technology. So we hope to always be available for that.
Maybe you could talk about the skull project quickly and how you produce those.
Yeah, I don't think I have the slides for that. But one of the things that we did print for a local, or for one of our profs here, was a fish skull. So she teaches an anatomy class for invertebrates, and she needed a model for every student to take home. Obviously, with COVID, you didn't want students sharing models, but the models that she was able to get are actual fish bone. So they're very fragile and they're kind of hard to get. They're several $100s. So we were able to scan that, 3D scan that, make a model that was an exact replica of the one she had on hand. And then we were able to print, what did we do? We did about 40 for her. And we were able to produce those in about 2 days worth of printing and about a day and a half of post-processing, which actually led us to producing several more, about another batch of 35 for a prof at WashU. So yeah, we definitely have the capacity, especially on smaller things, to scale up and produce a lot of them fairly quickly.
So yeah, you saw the build volume of the printer when we looked at the mask. So if you have an object that's the size of the mask, then we can print. If we went full time, we could print 2 of those batches a day. Is that correct? One in the day and one in the night. So produce 18 or 20 units a day.
Yeah, that's correct.
Something like that for something that size. And if it's half that size, then we can produce 4 times that many.
Wow, that's really cool. All right, what other questions are out there? Give it just a second here for everybody to think of something if it's on their mind. Don't forget to take off mute if you're interested in asking a question.
You know, that church project that you did with the scanning of the whole building was super interesting to me, but I'm not sure that I fully understood the high level details of how that actually transpired, how you take a scan that you do in real time and make that a physical structure. Could you talk a little bit about that?
Yeah, so there's several ways that you can do it. We've actually gone through a more manual process, but there are some programs out there that have automated it. But basically what LiDAR is it shoots out light beams, and then the way those get reflected back to the detector helps you determine how far that spot is and what color it is from the camera. So once you fly around, that drone has GPS on it. So every time you're logging data points, you're comparing that to the GPS coordinates that you're at. And that's how you're building up that model. So you've got all these points that come out. We're going to overlay a mesh on there. So we're going to connect all of those points to each other so that we get a nice surface. And then we're going to build out that surface into a volume. So then we can take that, we can translate that into something the printer can read. We can either take it with color or without color, depending on which printer that we're wanting to print it on, and we can make that physical model. And even if you guys don't have a drone, but you're interested in some space, there's a massive project right now through, oh man, who's that through? One of the government agencies, I can't remember which one, to actually go through and LiDAR map a lot of the United States. So there's all of the national monuments and the national parks all have LiDAR data out there already for you that's available. So if you're looking at any of those interesting spaces, a lot of cities have companies that are coming through and mapping the entire city. Obviously not to the detail that we took of the church, but obviously good enough that you could make 3D models of any part of the city that you want.
That's really interesting. Okay, good deal. I would ask that we get a picture of the group today. So if your camera's off and you're interested in being in that picture, we're gonna get a little snap of a picture here in just a minute. But while everybody's kind of teeing that up, if you could turn your cameras on, are there any other questions out there that anyone may have? All right, well, Andre, Mike, Andy, this has been really fascinating. We really appreciate the opportunity to for you to come in and demonstrate this to the group or show this to the group. And we wish you the best of luck in everything. And thanks for being here today. And thank goodness you made it through COVID, but this is really, really cool stuff.
Yeah, thank you for your time. And if you want to reach out or just come see the space, it's a cool space to look at. Even if you're not interested in using it, it's always cool to see. So feel free to stop by or drop us a line.
Awesome. Well, we're going to get 2 pictures here, folks. The first one will get of room 1. The second one will get of room 2. So if you can give me a nice smile on screen here, we'll get things going. All right, give me 1 second. That is room 1, so you don't have to have permagrin on. And give me 1 more second here. We'll switch over to room 2. And room 2, and I know it's hard maybe to tell what room you're in, but if you could smile, room 2, here we go. All right, we got them. Okay, so you can continue smiling, of course, if you want, but you can also stop smiling if you have permagrin.
Hey, Tom, could you share the email to contact them with again?
Yeah,
Send it out later.
Yeah, the emails for the 3 speakers.
Yes, please.
Yeah, absolutely, Larry. We'll get that out to the group in our thank you email. So just a couple things here. Thanks, of course, to our sponsors who make all this possible. So I see a few folks online here. Lapata Flegel, Mike Weiss, and Mark Whittinger from Lapata. Thanks for helping us. I don't think they could make it today. And if you are online, just wave. CMA, Jamie Wolf, I see is on there. Thanks, Jamie. Parkside, David Kennedy. I don't think he was able to join us today. Black Twig, Tom, I see you up in my left corner. Thanks for being here and everything you do. Atomic Revenue, I saw Steph Hermanson on a little bit earlier. Thanks for being here. Polsonelli, Paul Kluge, thank you for being here. And of course, for the background from work from Jason over at Swip Systems and our gang over there. Thanks for all the help there. So thanks to all of them. Give them a round of applause if you could, please. If it weren't for them, we wouldn't be here today. So thank you for everything they do. This will be a little bit hard for anybody who is not on video, but by show of hands, how many people would be up for an in-person event around the July 9th timeframe? Okay, good deal. Looks like we've got a few people that are ready to get out of the house. So I'm right there with you. So in between, our next virtual networking event is going to be on June 4th at 6:45. So it's about 2 or 3 weeks out, I believe, from right now. So June 4th, 7:45. Sorry, I said that wrong. 3 weeks from today, we'll do another pure virtual networking event. That might be our last one. We'll just see how things go. And then on July 9th, that will be our in-person event then. So as long as everything keeps trending in the direction that it is and everything keeps going, then we'll get together on July 9th out at the DePere Lodge. The room is reserved and ready to go for us. So we'll be meeting there. And we may even provide a virtual option for that, depending on how things are going. So thanks to everyone. Thanks to our sponsor. Thanks to Andre, Mike, and Andy for being here. We really appreciate the information, and we'll make sure that we disseminate those email addresses out to everyone. So thank you. We hope you have a wonderful weekend. Really appreciate all of you, and take care, folks.
Thanks for putting this all together for the last 50 episodes, Tom. We certainly appreciate it.
Our pleasure, Vic. Yeah, it's really a fun thing to do. It's an awesome way to give back. So thank you for that.
Bye.
Bye, everyone. Thank you so much.
Bye, everybody.
Bye.
Take care.